Okay, so we've been studying analysis of graphs, right? We studied critical points, or minimum, maximum. We studied increasing and decreasing, and end behavior, right? And how to calculate all those using your calculators mostly. Okay. Continuity is one of the biggest concepts that we have in math. It really requires calculus to fully understand it, but we can do it in pre-calc to a point. Okay. There's something in calc we need to make this formalized. But, if you were to draw a graph that was continuous, so go ahead and draw a graph on your paper that you think is continuous, without even knowing what that is. Just intuitively, do you think you know what it is?
Just draw a line.
It doesn't have to be anything specific, just draw some function that's continuous. And then I'll draw one up here and we'll see if they match. As far as continuity is concerned. You got one drawn? Here's a continuous function. What does continuous mean? Yeah, continuous. Somebody said no breaks. Okay, anybody else have any other way to describe it? That's a pretty good way. Huh? It can end. So as long as you define a domain, you can stop a function. Okay, so we can be continuous on a domain. Like square root of x is continuous from 0 to infinity. Right? But if we said on all real numbers, root x is not continuous, it stops. Right? So no breaks. If you draw it with a pencil, you don't pick your pencil up. Right? That's the big idea. Pretty straightforward. There are three types of continuity, discontinuities that we studied. Okay. We have a what might you call that? Discontinuity, what kind?
Jump. No.
Point? Somebody said point. That's point discontinuity.
I saw this on the book.
Yeah, it's in there. Some of you have already tried to do some of these, which is fine. So that's a point discontinuity because it's just there's just a hole at that spot. Okay. What else can we have?
Infinite.
Okay, we could have an infinite discontinuity. Do you want me to draw another one? Separate?
Sure.
Thanks.
No.
Let's put it over here. So I have too much going on one graph. That's an infinite discontinuity. Okay, there's one more. Most often pops up with piecewise functions.
Jump.
The jump discontinuity. Okay, those are the three types of discontinuity that we'll study. jump. Huh?
Michael's speakers.
Continuous functions are very important because they give us a lot of calculus. They give police officers the ability to give you a ticket while riding in a helicopter above the highway. Yeah. When you're driving, if you drive from here to Denver, is that a continuous function if you map your route?
Yes.
Can you ever have a jump discontinuity? You could come off the road, right? But you're still traveling towards Denver. You still have a route, right? Okay, so continuous functions allow cops to give you a ticket while timing you from a helicopter. Okay, that's something you study in calculus.
So with the point
I don't even know that
pulling off and exiting
They wouldn't
right
do
back
that
on
instead.
highway?
But you would have to not cross a point at somewhere. That's the problem. So that's not possible. Yeah, but you're still going towards Denver and you're still, it's a three-dimensional map this time, right? You still have a route. Okay, so there are 2 items that you need. Let's call it 3 items that you need to show. So we're going to show how a function is continuous at a point. Okay. So if I wanted to show that function is continuous, what has to happen? You're looking at your discontinuities.
You need arrows.
Okay, does this point have to exist?
Yes.
Okay, so to be continuous, this is more official. The point exists. Okay.
Does this apply to all of them or just the point one?
Okay, so we've solved this issue, right? If the point exists, we don't have a point discontinuity, right? Okay, how do we solve that issue?
I have a question.
Yes.
Does it matter if the circles are filled in or open? For any of those points?
So does the point exist here?
No.
But does it exist here?
Yes.
Yeah, so far, this is satisfied, right? This point exists. Okay, that is open, but this one's closed, so that point exists right there, right? There's a spot on that x value. Does that answer your question? Okay. So the point exists at that spot. Okay, but how do I solve the fact that there's a break here? How could we mathematically show there's no break?
Isn't it in the same like x value? Is it on the same like x value? You know what I mean?
So you have an x value, you mean the same, I think you're on the right track.
Like it's in the like y value? No.
You need the same y value, right?
Yeah.
From both sides?
Oh yeah.
Okay, so, yeah, this side has to come to the same y value as that side, correct? And that would join the functions together, same y value? Okay, so, the function has the same y value from both sides. Is that a good way to put it? It's not very mathy, but does it make sense? Okay. So that takes care of an infinite or a jump discontinuity, right? Okay.
Is a parabola continuous?
What do you think?
Yes.
Well, I guess. Yeah.
Oh, wait, no.
Does every point exist?
Yeah.
And are there any breaks in it?
No.
No. Yeah. So yeah. There is a function over there that is not continuous.
Y goes halfway or 1.
1 over x, the rational function, is not continuous at x equals 0. Right? Is that an infinite discontinuity? Okay, so that's like in general the big idea of continuity. Okay? No breaks. So let me walk you through how to do this mathematically. How do I show a function is continuous mathematically? Okay. All right, let's see what's in the book. We can always make a order with this sometimes. Do you want to do an easy function or a hard one?
An evil.
Okay, pick one.
Easy one.
Show, pick a function. No, a function, pick a function.
X squared.
Okay. Oh, you get it. Is continuous at x equals what? 3? I heard 3. Okay. It's a 3-step process. To show a function is continuous at one spot. What was our first criteria?
An evil point.
How do I show a point exists?
At 3.
F at 3 is? 9.
Oh.
Point exists. You don't have to write point exists, but that's just a note. So that's the first step, is just to plug it in and see if the point exists. Okay. If that does not spit a value out, the function is not continuous. Okay? Okay, here's the part that takes some time in PreCalculus. Calculus makes this really fast. We have to show that the same y value from the left and the right. So, if you drew this, you would see that from the left side and from the right side, they both go to 9, right? Okay, but how do you mathematically show that using numbers? Okay, graphically, it's there. Okay, but how can we solve it, show that numerically? We have to use a table of values. Okay. Calculus allows us to avoid a table, which is kind of nice. 3's in the middle. What's a number really close to 3?
2.
A decimal.
2.9.
Okay, let's start with 2.9. Is there a number closer to 3 than that?
2.99.
And we're going to show it with 3 numbers. Is that to the left side of 3?
Yes.
Are we going towards 3?
Yes.
Yeah, so we're going to show that these x values go to 3, so do the y values go to 9. Okay, so this is just a function in the calculator. Okay. The calculator makes it pretty easy. So we just plug each one of these in and see what the numbers give us. Okay. Okay, you know what an emulator is? It needs a ROM. Okay, so let's try 2.9 squared, right? $8.41. Sorry, it just reminded me of a movie. Major Pain. Okay, and we're going to 2.99. Of course, we can't repeat the phrase that it follows, but. And then 2.999.
Is that 8.1 or 8.1?
4-1. What are those numbers going towards?
9.
They're going towards 9, right? Okay, so from the left side, we're approaching 9, correct? Now, how would we do the same thing on the right? What numbers are we going to use?
3.1.
Yeah.
3.1.
0, 0, 1, 0, 1, and 3.1. Okay. And we're going to do the same thing. And we're just going to see if they both go towards 9. Okay. And then 3.0. Okay, and 6106 and 06. So those go towards 9, and those go towards 9, right? We can conclude that that function approaches 9 from each side. That's supposed to be an arrow. Okay. So that's the second step. It always takes the longest. Okay. So we've taken care of a possible point discontinuity, and we've taken care of jump and infinite discontinuities, right? All those are addressed. We just need to make our statement. That's our third step. Okay. All caught up. Since, so this does not have to be your exact wording, but has to include all this information in a sentence. F of 3 equals 9. Okay, that's number 1, right? And F approaches 9 from the left and right of 3. F is continuous at x equals 3. It's some statement of that nature is what you need to have. And like I said, it doesn't have to be exactly like that, but it can definitely include all that information to write a good English sentence. Okay.
Your stats literally had like paragraphs, and you have the right answer, otherwise you get your point.
Yeah, we have similar, they're not as scripted in calculus, but statements like that, we make that statement in calculus a little easier, it's easy and shorter. But, yeah. Questions on showing continuity? Okay. Do you want me to show you some functions that are not continuous, just to give you an idea of what we're looking at? You might have more complicated functions than that. It's just the same process. Okay, let's look at Okay, F function there. Is it continuous at x equals -3? Why?
Because, X came first, the denominator is 0.
Okay, so how do we say that continuity, what step did it violate? 1, 2. Yeah, step 1. So we need to plug in -3 and show it gives us something that doesn't exist, right? So f at -3 is -3 over 0, right? And you would say, since f at 3 is undefined, f is not continuous. And you can abbreviate continuous, makes it easier.
Yeah.
Okay. They do accept that on the AP exam as well, because we know exactly what you're talking about. So you make some sort of statement, right? What kind of discontinuity is that? You know what this graph looks like, right? Yeah, that's an infinite discontinuity. Okay. That's an example of an infinite discontinuity. Jump discontinuities are most commonly encountered with piecewise functions. Do you want a piecewise function on there real quick?
Sure.
Here's a piecewise function that is not continuous. So at x equals 2. So see, this is where our break is, right?
Yeah.
So that's where we're going to analyze continuity most of the time.
Gotcha.
Okay. So does f at 2 exist? And which one of these do we use? Which one has the equal sign in it? The bottom one, so this is where we use f at 2. Right? Okay, so step 1 of the continuity test is 0. Okay? So we just star that, use 2 minus x. That's the bottom one, right? Okay. Now we need to figure out left and right, correct? These are a little easier. Actually, you don't have to do a table of values if you don't want to. On a piecewise function, which one of these is the less than function?
The bottom one?
Yeah, that is 2 minus x, right? So And we're gonna plug 2 into that. That's 0, correct? Okay. And then the right-hand function is greater. Okay, that is the 3x minus 2. So 3 times 2 minus 2 is 4. Correct? Okay, I know I'm moving fast. You don't want to be skewed by the middle. You're going to be safe by the middle. Are those numbers the same?
No.
Different. So we have different numbers from the left and right. That implies a discontinuity. Discontinuity.
Which discontinuity is it?
This is a jump discontinuity. Because we have actual numbers there, right, 0 and 4, and there's a break. If it was like, if those spit out infinity and negative infinity, like this, we would know it's an infinite discontinuity. Okay. But obviously, plugging and chugging for us as pre-calc students, infinity, negative infinity doesn't really make it work. So, again, calculus makes it easy. Okay? Okay, I think that covers us. Any questions? Okay, again, not most exciting thing ever, but it is important. So, we're good. Do you have the homework written down already? If you don't, it's on Google Classroom. Okay, 3.5 and 3.6, all in one thing, due tomorrow. This was the last piece of it.